In the last video, we derived our first differential equation, dy dt is equal to negative py. In this video, we're going to solve that equation. But in order to do that, we're going to have to do something you were probably told you could never do. So let's get into it. So let's start by taking a closer look at the equation dy dt is equal to negative py. Let's start by examining the left-hand side, which says dy dt. What does that mean? Well, that means if we have a function of y, which we take the derivative of with respect to t, it's equal to some function. So for example, if we have the equation y is equal to t, then dy dt is the derivative of t, which is equal to 1. We could also replace the y with a y of t or even an f of t, though whenever we write differential equations, it's very common to leave off the functional notation and simply leave it as the variable y, which takes us all the way back to algebra, whenever we would always write an equation as y is equal to some expression of x. And along the way, we stopped doing that, and most of us forgot about it, until now. So just keep in mind, though we see a y, it actually represents a function of some kind. And that function describes the behavior we want to model. So going back to our differential equation, we're saying that the derivative of the function we want is equal to negative 1 times p times y, the function we want. So how do we find out what function that is? This is the part we'll have to ease into and take a closer look at the dy dt expression itself. You're probably familiar with integration, and remember that whenever you draw out an integral, it's usually concluded by a dx or a dt or a dsum variable. When we first see this, it usually feels a little odd, but if we think of the integration as a summation instead, it makes a little more sense. So let's say we have a function of some kind, and we want to integrate between a and b. And remember, integration is just a way to calculate the area. So the standard Riemann sum will do the trick, where we slice that region into tiny rectangles, and then we calculate the area of each rectangle by just multiplying its width times its height. So in this case, going from A to B, if we want to chop that into g many pieces, we'll have to determine the width, which is going to be W is equal to B minus A divided by G. So in order to calculate out the area, it's simply the sum of the width multiplied by the function with the input value of a plus wn, where n is the index, which ranges from 0 to g. Now, if x is our independent variable, we could also call that width a delta x. If we're able to chop that region into infinitely many pieces, then each width then becomes from delta x to dx, which we call a differential. A differential is an infinitely small change in some quantity. So by that logic, what does dy mean? Let's take a look at this diagram here. Here we have the curve of some function that we're looking at, and we have a point for which we've drawn a tangent line. That's the derivative at that point. Take a small step forward of the size of delta x, and then from that point upward to the function, we'll call that delta y. So let's pretend that we could get our delta x very small, smaller and smaller, as small as we need it. But keep in mind, if we're doing this manually, we're having to choose the size of our delta x. That means that it actually cannot get down to some infinitely small value. But let's say we choose a size that works well enough to give us the accuracy that we need in our calculations. In that regard, we could call it dx. So what then is dy? Is it just the height up to the function after taking a step forward of our now dx? Well, no. Take a closer look at this tangent line. As you can see, delta y is the height all the way up to the function. However, the tangent line intersects that. The section below where the intersection occurs is our dy. That way, we could interpret the tangent of the angle as dy over dx, and that's the derivative. So in general, dy is usually never equal to delta y. So what does all this have to do with our differential equation? Well, for one, it lets us know why they're called differential equations, because they include differentials. And it's a helpful way to think about a derivative. Why is that helpful? Well, for example, let's say we have some function that we want to take an indefinite integral of. Let's say it's the function y is equal to x. We could actually interpret that process as taking the reverse differentiation, in which case we're going to say that some derivative of a function is equal to x. So instead of saying y is equal to x, we'll say dy dx is equal to x. Now here's the part you've been advised against doing. Let's move the dx to the other side to give us the equation dy is equal to x dx. Now, let's integrate both sides to get the integral of dy is equal to the integral of x dx. Of course, the right-hand side is something we've seen plenty of times, and we know that that's just x squared over 2. But the left-hand side, well, that actually looks like something we've seen before too. It's just 1 multiplied by dy. We integrate that to get y. This approach feels much more intuitive and natural and explains where we get this dx from. Although, you've been told not to do that. And that's because if we treat differentials as a fraction all of the time, we run into some problems. But, in general, if we could represent a function as dy dt is equal to some function of y multiplied by some function of t, we could just divide one out and move it to the other side and solve it. Let's take a look back at our differential equation. Taking a look at our equation dy dt is equal to negative py, let's go ahead and move the dt to the other side. But let's not stop there. Let's now move the y to the other side as well, so that we have the variables of y on one side and the variables related to t on the other. Since t does not appear in this expression, then it's basically negative p dt. So some constant times dt. And just like in the example before, we'll go ahead and just integrate it and then solve for y. Doing that gives us the log of y plus c is equal to c sub 2 plus negative pt, where c and c sub 2 are two constants. Let's move the constants to the side with the negative pt, then exponentiate to get y by itself. That results in y is equal to e to the c plus c sub 2 multiplied by e to the negative pt. We could just write that e to the c plus c sub 2 as some constant, let's call it a. Ultimately, we get y is equal to a times e to the negative pt. That's the solution to our equation. So you might be wondering, what is that a? How do we find that out? Well, it turns out that this solution is extremely generic to a large range of situations and problem types. And therefore, a will represent something that we need it to for our particular situation. So if we were to take a look at the game that we had set up, if we were going to start with 60 dice at the try 0, let's put 0 in for this try, we get y is equal to a times e to the 0, which is just y is equal to a, which we know is 60. And for the game that starts with 10, we do the same thing. When we solve a differential equation by separating the variables in this manner, we're performing a technique called separation of variables. The mathematical justifications of this basically look exactly like what we just did, but adds in some steps, which to most people feels like circular reasoning, so I won't get into that. So now's the time where we actually play the game and then compare the results we get to our theoretical expectations. In addition to that, let's go ahead and compare the two games, the 60 dice, 20 tries, versus the 10 dice, 8 tries. So as a quick refresher, here's how the game is played. Starting with either 60 or 10 dice, you pick a number between 1 and 6. The dice are then rolled, and then dice matching your number are taken away. You pick another number and try again. For the 60 starting dice, you have 20 tries. For the 10 starting dice, you have 8 tries. Your goal is to get the dice count down to either 1 or 0, otherwise you lose. So let's take a look. So starting with 60 dice, that's going to be 60 multiplied by e to the negative 1 over 6, the probability of coming up with any number from the die, multiplied by x Again, we see that's 60 and it gradually goes down exponentially. Then the next one would be 10 times e to the negative 1 over 6 multiplied by x. And these are our models. Now I also input the real information that I got from playing it. So let's take a look at how that looks. Here's the game starting at 10. And in fact, you see it does quite match our expectation. Now starting at 60. Again, that also matches quite closely what we expect. So let's see how likely is it that we're going to win. So let's zoom in. For this one, we had 8 tries. So whenever we're getting down to 8, the amount of dice that we can expect is going to be about 2.5. Let's either round that up to 3 or round it down to 2. So we're very close to winning, very close. In fact, if there was just a little bit of luck, we might actually win. And for the 60 dice, we had 20 tries. So what do we expect there? Well, let's go down. We expect there to be about 2. So it looks like the chances of winning either one are very similar. Now on the surface that might feel odd because the try count and the dice count do not track linearly with each other. So we could say multiply 6 by 10 and get 60, but we do not multiply 8 by 6 and get 20. That's because the behavior is exponentially decaying. So I did play this game quite a bit and I only won once. I have to point out that this exact same kind of math can be used to solve an enormous amount of real-world problems. We're going to go ahead and we're going to apply these concepts to solve a real-life problem. And, well, that's going to have to wait until next time. Before you head off, don't forget to like and subscribe, and definitely don't forget to go to mymerchoutlet.com where you could get tons of great stuff, including dice to play, dice 'em down. Again, that's mymerchoutlet.com.